Welcome, this is the AP Physics video lecture covering the law of motion. This is Pulleys part 2. We are going to compare the Atwood machine. Here you see this Atwood machine of two hanging masses from part 1. One mass is hanging on one side, the other mass is hanging on the other side. This is the force here. We saw that M1 is heavier than M2, or it has more mass. So the force of gravity here is going to be positive, and the force of gravity on mass 2 is going to be negative. The reason why is because we saw that going up it's negative and it changes direction. So here it keeps wrapping around, hence why the force of gravity is going negative for force of gravity on mass 2. So we saw that the summation of the force for the system is equal to force of gravity on mass 1 minus force of gravity on mass 2. The F cis can be look at the mass cis times the acceleration cis, and if we substitute that in, and we should get that the acceleration of the system is equal to m1 minus m2. So this is a difference in their mass times gravity. This here is the force, total force of here, and on the bottom is your mass of the system. That's what they're having here. And the forces right here is in this problem is only due to gravity. Now we are going to look at a modified Atwood machine. One of the mass is hanging and the other one is on a surface, and the surface is frictionless. We should label the free body diagram. We saw that first of all there's tension. They're the internal forces. They're going to cancel out. Notice they are the same length. There's a force of gravity pulling down on M1. Yes, there is a force of gravity pulling down on M2. It's right here. Force of gravity on G2. But the normal force here is equal to force of gravity 2. So here these two will cancel out. Hence why the only forces in this problem are your force of gravity on mass 1 is the only force left here. If we simplify, you should get acceleration of the system is equal to just mass 1 times gravity, which is, that's again the force of gravity, and the only force of gravity is on mass 1 because mass 2's force of gravity cancels, divided by the mass of the system, which is m1 plus m2. Now we are going to go to this website and enter these values, and we're going to look for the free body diagram. This is how the website looks like, and the instructions here ask me to set the mass 1 to 5 kilograms, mass 2 to 5 kilograms, and theta, the friction is equals to 0, and the angle here equals to 0. Okay, that's what we should have. It says to check on the free body diagram, which is right here, and then we will hit run. Okay, show the free body diagram. All right, so we saw here that the only forces acting on the system, I could hit reset, pause halfway, we would, and show the free body diagram, that the only forces here that are acting on this object is the force of gravity that is pulling it down. Okay, and there's a question 2, question 3, and question 4, right? So we did question 1. It says the only force is the force of gravity on the hanging block, and it goes down. We saw that in our example. All right, reset, run again. See, the only force here is the force of gravity, and that is what is pulling it down. That's M1G. We saw that. Next, check the show numerical value. So check the show numerical value, and I'm going to reset it, and I'm going to hit run, and I'm going to get some calculations. All right. So my acceleration here was 4.9. My tension is 24.5. My t equals to 1. My velocity equals 4.9. We should already see that is our equation for the acceleration. So if we plug in these values, we should get the acceleration of 4.9. We should see that the tension comes from the acceleration times the mass. So 4.9 times 5 should get you the tension. Time and velocity, time is given just in the problem because that's how long it takes for it to fall. And velocity, you can calculate velocity using your kinematics equation. V equals to AT plus V naught. Now it says to double the hanging mass by setting M1 equals to 10 kilograms and hit run. What do you think will happen to the tension force? Let's take a look. So we increase this to 10 and we hit run. Now we will see that the new acceleration is 6.5. The tension is 3.2. The time is less and the velocity is 5.4. So that's what the values are here. Now let's analyze these values. Why is the acceleration more? Well, if M1 goes up, the acceleration has to go up. It shows it right here. There's a direct proportion. If we double the mass, the acceleration of M1, the acceleration double. Right? More or less, well, because there's also the M1 down here. Okay? So, so the acceleration still went up. Right? Then the tension also will go up because the acceleration goes up. Okay? Because tension is equal to mass times the acceleration of the system. Time is going to go down. The reason why is because you're going to have a faster acceleration. So it's going to travel. You're going to travel the same distance quicker. So the distance that the block fell right here, the distance that it fell was the same distance, 2.23. It traveled that distance, but this time it accelerated more. The fact that it accelerated faster and traveled the same distance, the time has to decrease. Because the time decrease, the velocity also has to increase. Okay. Now let's set it back to default. So the mass here goes back to 5. But they say here, set it to default. So this is the default setting. Then it says double the sitting mass. So that's M2 to 10. What is going to happen? We hit run. Well, it still accelerates. Okay. All right. Same distance. And we get this acceleration. So let's see if this makes sense. Well, if the mass of M2, which is on bottom, increases, okay, because this is in the denominator, the acceleration also has to decrease, okay, because if it's in the denominator, it has an inverse relationship. So this makes sense why this dropped. The fact that acceleration dropped, the tension should also drop. But why is the tension here greater than, oh, did I type it in wrong? Oh yeah, I typed it in wrong. It's 3.27. Okay, so if I hit run, reset, run, it's 32.67. Yes. Oh, it's the same. So the tension here is the same. Look, the tension is the same. The tension is the same. Okay. The reason why the tension is the same, even though the acceleration is less, okay, is because their internal the acceleration and the because the tension equals to mass times the acceleration of the system. Okay, the mass here became 10 kilograms. So that's why the acceleration, the tension would be the same. Time, okay, the fact that the acceleration is slower, so the time is going to increase. So this is slower acceleration. Same distance. So therefore you're going to have more time. Okay. And the fact that you have more time, your velocity is going to be slower. All right. Good. Let's look at this concept question. Here we have this problem. So this is a modified Atwood machine, and it says block X of mass M is attached to block Y of mass 2M by a light strain that passes over a pulley of negligible friction and a mass as shown above. In which direction will the center mass COM of the two blocks move after it is released from rest? What is the magnitude of the acceleration of the block of block A? Well, if you take a look, we see in this problem before, the heavier mass is going to drop, so it's going to go down to the right. So the only thing left is A and C. So we can knock off this one. Okay, it won't stay at rest because there's a difference in the mass here, right? And it's frictionless. So this is the acceleration of the system is given by this equation. Look at the previous slide for how we got this. We plug in the values and I simplify. The m's here cancel out, so you have left 2g over 3. That is how they got the value of A. Okay. The COM just refers to the mass of the entire system. That's why it's like the center of mass. All right. Now, we've seen this before, but now this time we're going to now add friction to the surface. So how does that change the equation? Well, first of all, there's the tension force. Nothing happened there. Those still cancel out. And here, force of gravity is right here. Okay? Like before. So that's how it looks like, right? That's how it normally calculates, okay? But this time we add friction. Okay. So it goes in the opposite direction of the velocity because the object is going to go down. So this slides to the right, so the friction is going to go to the left. It is the opposite to that. So you're going to be minusing the force of friction on mass 1. What is that? What is that calculation? Well, it's mu normal force, and the normal force here is m2g. So the normal force here is n. So n is equal to m2g. Force of friction is mu n. So force of friction is mu times m2g. That's how I got that value. And we derive. Notice the only difference between 2 and 3 is that now there's going to be a minus mu on the block that has friction. So mu m2g is the force of friction here. That is how the equation gets modified. All right, so now let's go back to our problem. And we are going to do a couple things. Let's go to the website. And it says here, we want M1 to be 5, M2 to be 5. Mu is 1. So mu equals to, mu equals to 1. And the angle here is still equal to 0. All right, so hit run. Okay, click show free body diagram, show numerical value, and hit run. And what is the tension? Wait, what is happening? What is happening? What is happening? Why doesn't the block move? Uh-oh, why doesn't the block move? Take a look. Well, that must be the force of gravity here that's pulling it down. If we see, right? Notice that the force of gravity is less than, so the force of gravity here is less than the force of friction. So it doesn't move. So the force of gravity is not strong enough to overcome the static friction because of this value. Notice that for the object to move, right, to move, so this, for it to move, m1g has to be greater than mu m2 times g. This is for it to move, right? This, when they're equal, is when it's at acceleration equals to 0, right? And it doesn't move, not move, when m1g is less than mu m2g. The force of gravity of block 1 is less than the force of friction on block 2. Now we want to adjust the value of mu to find the coefficient that will allow the system to accelerate. So let's take a look. So we saw here it won't move. So what about if we just decrease it? Wow, if we just decrease it less than 1, look, right? At 0.99, there's an acceleration. It's slow, but there is an acceleration. You see how it's moving? As I decrease it more and run, there's more acceleration, right? So we would say the answer is mu is less than 1. How can we prove that? Well, for it to move, this has to be true. Okay? Right? So if we look at this equation, m1g is greater than mu m2g. Right? The g's here will cancel out. Then you divide the mu over. So mu is going to be equal to m1 divided by m2, right? So we saw that if it's mu has to be greater than, or no, mu has to be less than m1 over m2. And in this case, it was 5 over 5. So here it has to be greater than, mu has to be less than 1, okay, for it to move. That's the math for that. Okay, that's why we saw it right here. It says now hit the default setting and hit mu equals to 0.27. So I put it at 0.7555 here. That's where it resets at. Good. Now it says if you hit run, the system will accelerate downwards. Let's hit run and let's see if it accelerates downward. Yes, it does accelerate. Which mass and how much would you have to adjust so that the system does not accelerate? Which one would I increase? Well, what happens if I increase? That's interesting. What about if I increase mass 1? Does that help? No, it's just going to accelerate more. I don't want to increase mass 1. Well, it seems like I should increase mass 2, right? Yep. So here it's at 5. If I increase it, the acceleration goes down, it goes down, it goes down. Whoop, right here. So it looks around at 6.7 kilograms. So I hit run. See, the acceleration equals to 0. So it doesn't move. So here, I increase mass 2 because that is what affects the force of friction, and let m2 be any value less than 6.8 kilograms. So that's what we have here. Okay, right? Anything else? And so for it to not move. Okay. Hold on. M2 has to be greater than or less than. So it goes really quick, then it becomes so it becomes 0 here at 6.7. If M2 becomes less, it accelerates, but it becomes more, right? It doesn't accelerate. So that's why we have to keep mass 2 less than 6.8. So how can we do this? Well, let's do some math here. It's like this equation. First of all, it's for it to move, so it doesn't accelerate. So we want like something right here. So m1g mu is, what was mu? 0.75 m2g. Okay, the g's here cancel out because they're both g's. and we want to solve for we want to solve for m2. So we would just have to divide it over. So divide 0.75 to the other side. You get m2 has to be greater than m1 divided by 0.5. And in this case, if we plug in the number 5 here, right? If we plug in 5, let's see if that works. So 5 divided by 0.75. Correct. So this value is roughly like 6.66 less than m2, which is close to what we got here. Okay? That's the mathematical way, right? So remember this. Good job. Next. Now, we've now looked at it when it is on a horizontal surface with friction, and we saw this calculation here. What happens now when we is on a ramp with friction? So what happens here? Ooh. So we saw that there's friction opposing it, right? But also the fact that it's on a ramp, there is the horizontal component, which is m2g sine theta, and the vertical component, m2g cosine theta. Remember, once it goes on a ramp, there's that theta value here. Okay, so there is the force of gravity. Oops, sorry. There's the force of gravity that goes down here, which is Fg. F on m2g breaks down into its component form. All right, so what is opposing this equation? Well, it's going to be minusing two parts. First of all, it's going to minus the first thing that's going to minus is the friction force on mass 2, okay, which is the red one. Then also it's going to be minusing the m2g sine theta here. So these are the two forces that are opposing the F2, the force of gravity on mass 1. Okay. So this should be, give me a second, this should be a 1. This should be a 1. Give me a second, I gotta change this. Discard. This should be a 1, yeah. This should be a 1, okay, because it's, right, because this is on mass 1 and mass 2. Good, okay, so, sorry about that. Good, good. Component form, subtract that. So the two forces that it's Fg1, yes, is the positive one. The two minus ones are the m2g sine theta and the force of friction on m2. Good. All right, perfect. Good. And here it breaks down like that. The force of friction here is mu times the normal force. The normal force is m2g sine theta. Okay, again, if you really want to see that, force of friction equals to mu normal force. The normal force is this. So it's mu m2g cosine theta. That's how I got it here. So the two forces that are going against the box going down, the force of friction, the force of gravity on box 1, the two opposing it is the force of friction and the sine part of the force of gravity here. Okay, take this time to write down those notes. Now we are going to go back to the website and then put these values in. All right, so let's, it says here the mass is 5 kilograms, mass 1 is 5 kilograms, mass 2 is 5 kilograms, so let's go to 5 kilograms here. The friction is 0.75 and the theta here is 20. Perfect. It says click on show numerical value and hit run. What the hell? The acceleration is 0. Why doesn't the block move? Well, the force of gravity is not strong enough to overcome the static force of friction and the sine part of the gravity of mass 2. This is the part here. This is the static friction part that is subtracting it. And this is the sine part of gravity. Okay? You should see it here. Right? It has to be strong enough to overcome that. Which mass and how much would you need to adjust so that the system does accelerate in the positive direction? Well, if it's in the positive direction, it has to go down, right? So we have to probably increase, let's see. We probably have to increase mass 1. Yeah, look, if we increase mass 1, yeah, oh, right here, look. Right, it's 0.06. So if we increase it, yeah, it goes more. So it seems like we increase mass 1. Can we do anything to mass 2? Let's see. If we increase mass 2, does it do anything to the acceleration? Oh, well, it does. Look, we could decrease it. We could also decrease mass 2. All right. So which mass and how much would you have to adjust so that this system does accelerate? Well, I wrote one of the answers right here. I can increase mass 1 because that is what affects the force of friction. In this case, I said that M1 has to be greater than 5.2. And we saw that here. Right? We saw that when this was 5, right? We saw and this was 5, no acceleration. And as soon as you can 5.2, right, greater than 5.2, do you see how it starts moving at 0.06? And they say if they want to see math, okay. So if you want to look at the math for that, for if it's at equilibrium, for it to be at let's say v equals to 0, a equals to 0, not v equals to 0. When a equals to 0, that means m1g is equal to m2g sine theta plus mu m2g cosine theta, right? For it to accelerate, so for it to positive acceleration, so positive acceleration is when this is greater than this stuff, m2g sine theta mu m2g cosine theta, right? Okay, because then this is going to be more. When this becomes more, okay, how can we do that? By increasing mass, all right? And you could solve for it. Or you could decrease M2 on this side, right? Because you know gravity would cancel, all right? Yeah. You could actually simplify this if you do some math. Let me see. It would be M1 is greater than G cancels, so you could factor out an M2 sine theta. Oh, sine theta. Oh, I forgot the theta here. Sine theta plus cosine theta. So, yeah. That's interesting. So, M1, you could either increase M1 or you can decrease M2. Good. So, that's the math justification. Now, let's set theta equals to 0. Right, that's the last part. It says, so let me show you the equation. Oops, sorry. Let's set mu equals to 0. So now it becomes frictionless, right? And we have an acceleration here, right? Let's hit run. So yep, there is an acceleration because it becomes frictionless. But the question says, set mu equals to 0, so the ramp is frictionless. Which mass and how much would you need to adjust so that the system accelerates in the negative direction? That means it slides down the ramp. If I increase this more, the acceleration goes up. If I decrease it, the acceleration goes down. So I could decrease the mass. Look. I could decrease the mass. All right? So, here's the answer. And that's how the equation breaks down. The equation becomes this because the mu part goes to 0. So this part disappears because it becomes frictionless, right? So you can either increase mass 2. So you can increase, so for this to move, M1G has to be greater than M2G sine theta. All right? So G's cancel out. So this is for it to move. So you could either increase mass 2 so that the sine part of gravity increases. So this part can increase it. Okay. Enough for it to slide down in the negative direction. Oh, so oops, sorry. So it should be this because it says this is for it to have a negative acceleration. Okay, yeah. All right. So if you take a look, this is what I mean. So this was back to 5, right? It says we're gonna try to have a negative acceleration. So this one has to get super large. Oh no, is it super large? No, pause. So let me decrease this a little bit to like 3, and then you see how this could be super large, right? Run. Okay, that's how you could do it. The best thing you could do is decrease this mass so this gets pulled more. So what happens is you're decreasing the force of gravity pulling it down so that the sine part of gravity on M2 is more. All right, so there you go. I understand it was a very long video, but this is everything that you need to know about all the different Atwood machines scenarios. And my recommendation is to play with this site as an interactive to just get really familiar with this. There's not a lot of calculations on this part on the AP Physics exam, just a lot of analyzing. All right.